Welcome to the lesson on differentiation of exponentials and logarithms. And before we get into the actual questions, let's just review a very brief history of something that we did in Algebra 2 and pre-calculus at our grade high school. So it says if you have $1 invested at 100% interest, how much money do you have after 1 year? Well, the amount of money you have after 1 year is the amount that you started with. That's $1. That's the starting amount, right? Times 100%, because that's what you have to start with, plus another 100%, because that's the interest, raised to the first power, because that is the number of years that you're investing for. So altogether, you have $2. So nothing special there. Next, what if the interest was compounded quarterly, meaning that it's compounded 4 times per year, but at 1/4 of the interest rate? Okay. Would you have more, less, or equal amount of money after 1 year? So in this case, after 1 year, the amount of money that you have is still equal to that $1 you had before, times 100%, because that's what you started with. But rather than gaining another 100%, you only gain 1/4, or 25%, and the balance to that, or the offset factor to that, is that instead of getting a compound of once per year, you get it compounded 4 times per year. So we can calculate this, and we get some number that is slightly larger than 2. So we get about $2.44. So that's better than getting $2. But what if the interest was compounded infinitely many times? How much money would you have? Well, we can't divide by infinity, that's just 0, and we can't raise something to an infinite power, that's just infinity again. So now we have to think a little bit differently, and we have to use these in terms of limit. So this is just 1 times 1 plus the number of times compounded is n times, right? And so it's dividing, the interest is being divided by n, it's being raised to the nth power, and infinitely many times we just take the limit as n approaches infinity. Okay, and you can try this on a calculator. You can punch in some gigantic numbers for n, and eventually you see that this approaches approximately 2.72. Okay. So it's like 2.7182 with some repeating decimals to it. Okay. And this here is about 2.72, but this very, very special number, very, very special limit, is the definition of E. Okay, so E is equal to that limit. Okay. So there we have it. That is a very quick and brief history of this one particular topic from what we learned in Algebra 2 and pre-calculus. If you have a hard time on this, you can look this up. This is section 3.1 through this is sections 3.5 and 3.6 of your pre-calculus textbook if you went to school at Everest. Okay. All right, so I'm going to continue on here and just work with this definition for a little bit. So that's one definition of E. Now, in calculus, sometimes it's helpful to write the limit of a variable as it approaches 0 instead of as it approaches infinity. Okay, so here's the big idea. We are going to rewrite the definition of E using the limit as some variable, and we'll call it something different than n. So as say h approaches 0 rather than having it approach infinity. Okay. So to do this, we're going to define h. So we're going to define h as being equal to 1 over n. Okay. So as n approaches infinity, we can see that h will approach 0. And so then we can sort of rewrite all of these definitions. Oh, and so E then is equal to the limit rather than using as n approaches infinity, we can say as h approaches 0, because these two are equivalent based on this definition of h. So as h approaches 0 of 1 plus 1 over n, but 1 over n is really just h, raised to the nth power, but n is really just 1 over h. So we're rewriting everything in terms of h, with the understanding that h is just 1 over n. And again, this is another definition, an alternate form of the definition of E. Just another form of the definition of E. So we have two forms here, one using the limit as a variable approaches infinity, and the other using the limit as a variable approaching 0. And we're going to use this idea a little bit later when we actually talk about differentiation of logarithms and exponents. Alrighty, and one more item here before we can actually get to the main point. There's a little bit of appetizer in our wonderful mathematical meal. Okay, these are just some refreshers, some reminders about the laws of logarithms. You have the product rule, or the product law. The sum of two logarithms is equal to the logarithm of their products. The quotient rule is saying that the difference between two logarithms is equal to the logarithm of their quotient. And then if you have a number times a logarithm, it's the same thing as saying the logarithm of that number, of having the logarithm raised to that power. Okay? And so again, these only apply to logarithms, and in all these cases they have to be the same base. Okay, so here I'm using log base 10 for all of these. Okay, so some ideas: the definition of E, the alternate form of the definition of E, and the laws of logarithms, so that we can now use these and apply them to the next part of our progression. Thank you for watching. Be sure to watch the next video. Have a wonderful day.